All right, so when you think chemistry, what comes to mind? Probably a lab, right? White coats, bubbling beakers. Well, what if I told you that's not the whole picture? Not even close. From the second your alarm blares in the morning to the moment you fall asleep at night, you're a chemist. You are commanding reactions and running the show. Let's walk through a day, and I'll show you how you're already a master of the elements.
So let's start with a kind of weird question. What could your breakfast, your toast, your cereal, possibly have in common with a gigantic roaring waterfall? Seems like nothing, right? Well, the answer is the one thing that gets your entire day started: energy. Okay, let's kick things off with the morning. Every single thing you do, and I mean everything, from just opening your eyes to actually getting out of bed, it's all about moving energy from one place to another. This is basically you every single morning. When you're lying there in bed, you're like a fully charged battery. You're just full of potential energy, stored energy. And the second you throw off those covers and start moving, boom, you've just converted all that potential into kinetic energy, the energy of motion. Okay, so you stumble into the shower. That amazing blast of hot water, that's an exothermic process. It's literally releasing heat to warm you up. But then you step out and you get that little shiver, right? As the water on your skin evaporates, it actually pulls heat from your body to do it. That's an endothermic process. See? Two different heat reactions, and you haven't even had coffee yet. But look, you can't run on empty, right? You need fuel. And that breakfast you're about to eat isn't just delicious, it's a package of chemical potential energy. And we measure that energy in a unit you see constantly: kilocalories. Or, as it's written on food labels, calories with a capital C. So where's all that energy hiding? Well, any nutrition label will show you these three big players: carbs, protein, and fat. Now, carbs and protein are pretty similar energy-wise. But here's the kicker. Look at fat. It's packing more than double the energy punch for every single gram. It's incredibly energy dense. So you ever wonder how they actually get that final calorie number on the box? It's not magic, it's just some super simple math. You just take the number of grams of each component, multiply it by its energy value from that chart we just saw, and then you add them all up. Let's just walk through the math for this snack here. And voila, there you have it. 165 kilocalories of pure chemical fuel, ready to be turned into kinetic energy to get you through the morning. Every time you glance at a food label, you're not just reading, you're doing thermodynamics. How cool is that? All right, so fast forward to midday. This is where things get really interesting, because you're not just using energy anymore. Oh no, you're actively directing chemical reactions. And the best lab to see this in action is, of course, your kitchen. I mean, think about it. Every time you cook, you're basically a chemist in an apron. Why do you crank up the heat on the stove? Because you know that increasing the temperature makes reactions happen faster. Why do you chop up your vegetables? You're increasing the surface area, giving the heat way more places to work its magic. You're controlling the speed of chemistry without even thinking about it. But chemistry isn't just about making things go faster. It's also about balance, or what a chemist would call equilibrium. Now, that word might sound a little intimidating, but there's this really elegant rule called Chatellier's principle that makes it all make perfect sense. It basically says that chemical reactions hate being stressed out and will do whatever they can to get back to their happy place. Seriously, the absolute best way to get this is to picture a seesaw. If it's perfectly balanced and you suddenly add some weight to one side, you stress it out, what happens? The seesaw doesn't just stay lopsided, the whole thing shifts to try and find a new balance point. So let's put our seesaw to the test with a real chemical reaction. If we add a bunch more nitrogen, the stuff on the left, that side of the seesaw gets heavy. So to rebalance, the reaction shifts to the right, using up that extra nitrogen to make more product. It just wants to get back to equilibrium. It's always trying to find that balance. All right, as we head into the evening, let's zoom in a bit. Let's look at the actual stuff you've been messing with all day. The molecules themselves. Pretty much everything you can touch or taste falls into one of two major chemical families. Just look at your dinner table. You've got sugar and you've got salt. Sugar is organic. It's built around carbon, and yeah, it can burn. Salt is inorganic. It won't burn, and it dissolves like a dream in water. Their most fundamental behaviors come down to this simple divide: organic versus inorganic. So if carbon is like the basic Lego brick for all these organic molecules, what makes them different? Well, it's all about these things called functional groups. Think of them like personality tags. They're little clusters of atoms that attach to the carbon backbone and give the whole molecule its unique identity and behavior. For example, sticking an OH group on something is what makes it an alcohol. It's that simple. Okay, but with literally millions of these compounds out there, how on earth does anyone keep track? Well, chemists came up with a system. It's a universal language with its own grammar for naming every single molecule so there's no confusion. Let's take a quick peek at how it works. Okay, deep breath. You don't need to memorize this, I promise. The point here is just to see that there's a system, a logic to it all. First, you find the longest row of carbons, that gives you the family name. Then you number the carbons so you know where everything is, name any little side streets or branches, and then you just put it all together in order. So when we put those rules into practice for this molecule right here, what do we get? We get 2-methylbutane. Butane tells us the longest chain has 4 carbons. And 2-methyl is a precise address, telling us there's a 1-carbon branch sticking off the 2nd carbon in the chain. It's like a GPS coordinate for a molecule. And hey, butane is the stuff in your lighter. You just learned its real name. So from the energy you burned getting out of bed to the reactions you controlled on your stove, your entire day is just one big, awesome chemistry experiment. And you're the one in charge. You've been commanding the elements all along. The only question is, now that you know, what reactions will you choose to control today?